In our technologically driven world, ensuring the correct behavior of systems is paramount. From the software controlling our cars to the complex networks managing our finances, the consequences of system failures can be severe. This is where temporal logic comes into play. Temporal logic provides a powerful framework for specifying and verifying the behaviors of systems over time. Imagine a traffic light system. We need to ensure that the lights never show green in both directions simultaneously, preventing accidents. Expressing such safety-critical properties requires a language that can describe the ordering of events over time. Temporal logic provides the tools to do just that. Traditional logic allows us to reason about static truths, such as all men are mortal. However, it falls short when dealing with dynamic systems where properties change over time. Temporal logic extends classical logic with operators that capture temporal notions like always, eventually, and until. The development of temporal logic has revolutionized how we design, analyze, and verify systems, particularly in computer science and engineering. Its applications span a wide range of fields, including software engineering, hardware design, and artificial intelligence, making it an indispensable tool in our quest to build reliable and robust systems. Temporal logic is a branch of formal logic that extends classical logic by incorporating time into its reasoning framework. Unlike classical logic, which deals with static truths, temporal logic allows us to express and reason about propositions whose truth values may change over time. In essence, temporal logic provides a language for describing the temporal ordering of events and the relationships between them. It enables us to formulate statements about the past, present, and future behavior of systems. For instance, we can express properties like the system will eventually reach a stable state, or whenever a request is made, it will be eventually granted. Temporal logic encompasses various formalisms, each with its strengths and weaknesses, tailored to specific applications and system models. Some prominent examples include linear temporal logic, LTL, computation tree logic, CTL, and M-calculus. The choice of temporal logic depends on the nature of the system being analyzed and the properties we aim to verify. LTL, for instance, is well suited for specifying properties over linear time, where time is viewed as a sequence of events, while CTL is more appropriate for branching time models, where multiple possible futures exist. Linear temporal logic, LTL, is a widely used temporal logic for specifying and verifying properties of reactive systems. In LTL, time is viewed as a linear sequence of states, capturing the system's behavior as a single execution path. Imagine a program executing step by step. Each step represents a state of the system, and the sequence of steps forms a linear timeline. LTL allows us to express properties about this timeline, such as the variable x will eventually become true, or the system will never enter an error state. LTL's linear view of time makes it particularly suitable for specifying properties related to safety and liveness. Safety properties assert that something bad never happens, such as the absence of deadlocks or the guarantee that a critical section is never accessed by two processes simultaneously. Liveness properties, on the other hand, state that something good will eventually happen, such as the eventual completion of a task or the responsiveness of a system to requests. The simplicity and expressiveness of LTL have made it a popular choice for various applications, including runtime verification, model checking, and system synthesis. Its ability to capture essential temporal properties in a concise and intuitive manner makes it an invaluable tool for ensuring the correct behavior of complex systems. The syntax of linear temporal logic, LTL, is built upon atomic propositions, logical connectives, and temporal operators, providing a language for expressing temporal properties. Atomic propositions represent basic facts or conditions that can be either true or false at a given time. For example, the robot is at location A, or the temperature is above 25 degrees Celsius are atomic propositions. Logical connectives, such as negation, conjunction, disjunction, implication, and equivalence, combine and modify the truth values of propositions, similar to classical propositional logic. Temporal operators are the hallmark of LTL, allowing us to express properties over time. Some common temporal operators include always /g, /ph, asserts that the proposition phi holds true for all future states along the timeline. Eventually, or f, ph states that the proposition phi will eventually become true in some future state. Next, or X, pH asserts that the proposition phi holds true in the next state along the timeline. Until, U, FUPS expresses that phi holds true until psi becomes true. These operators can be combined to express complex temporal relationships. For instance, here request grant states that always, if there is a request, it will be eventually granted. Section 5. Semantics of LTL. The semantics of linear temporal logic, or LTL, define the meaning of LTL formulas concerning a system's behavior over time. In essence, we interpret LTL formulas over infinite sequences of states, representing the system's execution paths. Each state in the sequence represents a snapshot of the system at a particular instant, capturing the truth values of all atomic propositions at that point. The semantics define how to evaluate the truth of an LTL formula over such a sequence. For instance, the formula always phi is true for a sequence if and only if the proposition phi is true in every state of the sequence. Similarly, eventually phi is true if and only if phi is true in at least one state of the sequence. The temporal operators like next and until define the truth of a formula based on the truth values of its subformulas in the current and future states. For example, phi until psi is true in a state if either psi is true in that state, or phi is true in the current state, and phi until psi is true in the next state. Formally, the semantics of LTL are defined recursively over the structure of formulas, providing a precise interpretation of each operator and connective. This rigorous definition ensures that the meaning of LTL formulas is unambiguous and allows us to reason about the truth of LTL properties concerning a system's behavior. Section 6. LTL Model Checking. LTL model checking is an automated verification technique used to determine whether a system satisfies a given LTL specification. It involves systematically exploring the system's state space, checking if the LTL formula holds true for all possible execution paths. The process begins with a formal model of the system, typically a state transition system, representing the possible states and transitions of the system. We then express the desired property as an LTL formula. The model checker systematically explores all possible execution paths of the model, checking if the LTL formula holds true for each path. If the formula holds for all paths, the model satisfies the property. However, if the formula is violated on any path, the model checker provides a counterexample, highlighting the sequence of states that leads to the violation. LTL model checking is a powerful technique for finding subtle errors in system